This is the video for the Trestle Dynamic Programming routine. Over here on the left is the first part of the routine, and here on the right is the last part of the routine. It starts out by moving numerically 100 values from pole placed to save placed. Then it fills numerically 20 positions at base cost with 0. That's to indicate when we start there is no back cost. Next, it fills the 20 numeric positions at back cost 20 with a very high number. The first pole it's going to look at is at offset 20. And here it says EG, which is going to be the offset it uses for the pole, is going to start at 20. Next it says for IG of 2, and down here at the bottom, IG to 98, one at a time. It's going to go around to the pole positions from 2 to 98. It's not going to use position 1 because that's right next to the beginning, that's too close. And it's not going to use position 99 because that's too close to the end. So it's going to go from pole 2 to pole 98. Next it says, set the test index to EG. Well, here's EG 20, and down here it adds the EG 20 each time, because that offset, there are 20 for each pole. So that value has to be increased 20 each time we go to a new pole. Then it says there to fill the best cost with a very high value. That means hasn't found one yet. And the 20 best indexes with 0. So what we're going to do down below here is find these best costs. Then we're going to set LG to the pole use sub IG. Alright, that's the pole position we're at. Set MG to the cost of that pole. So as we work down below here, we're going to know that MG is always set to the cost of the pole at this particular position. Next, we're going to go back up to 20 positions. We're going to, for JG equals 0, and down here, next JG to 19, one at a time, we're going to go back to previous pole positions to get a back cost. We're going to set our test cost here to the beam cost for going back that distance. And each time that's going to increase because JG is going to increase and be a stronger pole. Stronger beam, I mean. Then it sets KG to the test index. Well, that's this value up here. Then it says add to that the back cost at KG. Remember, we're going back to previous poles. Here it's getting this test cost from the previous pole, and it adds to it what we saw up here was the cost of the pole. So now we have a test cost that has the cost of our pole plus the cost of going to a back pole. Now we're going to go around a loop on LG for LG of 0, and here next LG 19. It's going to go around this loop 20 times. This loop, though, is for finding the cost for having a particular strength going forward. What I mean is that now poles that come after this pole are going to come back to this position and say, I'm so far away, I need a strength. And I want to ask for a certain strength for a beam. I want you to give me the answer when I give you the value of the offset. So here is we're starting with LG of 0, and we're going to go to 19. It's going to remember 20 strengths. So when it's asked about a particular strength, it can tell it what cost it will be for that particular strength to go back to the beginning. Alright, so It starts out with the test cost that we know we already encountered here for going backwards to a pole, and what it costs for this pole. So it puts that in dg. That's the cost of going back. Then it sets fg to that offset, adds to it this offset of going the other direction, and says, well, if that's what you're doing, then the base cost for this pole is the sum of those two, fg, and it adds that to dg. So now it has a particular strength for going the other direction. It has the cost in dg. Then it says, is dg greater than the cost I already know for doing this? If it's greater than, it goes to AL and ignores it. But if it's less than, and in this case even equal to, it sets the best cost for LG at the DG value. Remember, that's the cost of being able to do what it's asking for. And then, because this is dynamic programming, it needs to remember the test index where it found this. So later on, when it does the solution to it, it can say, well, I have this index to go back to. Where is it at? And here it'll say. All right, then it goes around that to 19 times, well, 20 times altogether. Then it knows the best cost for this pole position to support any beam coming from the future coming back to it. It knows the best cost. This is dynamic programming. It's solving this small problem of at each pole position what is best, so that later on it can solve the whole problem of how to get back to the beginning. And here it saves that information. Down here is the list where it saves it. It saves all the best cost and back cost, e.g., the 20 of them. Remember, e.g. gets advanced by 20 each time, so there's space to put it in there. And it also moves the back index of e.g., the best indexes. That's what it was creating here, so it knows how to go backwards. Then we go over to the other side here. It sets the lowest cost to a high number, and it adds to e.g. 1. Then for jg of 2, and down here we have next jg to 20, one at a time. We're going to go around this loop and find out what the lowest cost is from starting at the far end and going backwards. Well, first it says it needs to know the cost of the beam at jg. We're starting out with one that is size 2. Shorter than that, you're not going to go back just one pole. So it sets that to the test cost. Then it adds to the test cost the cost it finds at that position back there, which is the EG position. It adds that to it. Then it says, is that greater than or equal to the lowest cost I have? Well, if that's true, it goes to AN and says, I'm not going to do anything. But if it finds that that is a lower cost, then it says our lowest cost is that test cost, and I must remember the value of EG. Remember, that's our index of going back through the poles. It just found out that EG was the lowest previous one. Well, now here it subtracts from EG 19. Now, we know that there's 20 for each one, but actually as it goes back further, it must go to a stronger position at that pole's position. So it says, well, I can't go back 20 because then I would go to the lowest strength. I got to go to one strength higher than that, so I have to go back 19. Then it goes around this for all 20 possibilities and finds the one that's the lowest, and it put its index in BG. Well, then it comes out of the loop when it finds it all, sets PG to the lowest cost. I don't know why that's there, but maybe the programmer thought he wanted to know what the lowest cost was and put it in that control register PG. Then it fills 100 positions at pole needed with 0. It's saying, I don't need a pole at any position. I'm zeroing them all out. There's 100 possible poles. They're all 0. Then it sets the previous index to that BG. Remember, that is the offset that it found up here was the best answer. So here it sets previous index to BG. That's where it's going to start. Then it says I'm going to set IG to that previous index. Then I'm going to divide IG by 20. Remember, there are 20 for each pole position. So it divides it by 20 to find out which pole position it's looking at. And then it says, well, then pole needed at that IG value, that IG offset is a 1. Notice all the others are 0, but this position is a 1 because it says that is the best position going back. Then it sets KG to the previous index. Wants to put that in an offset register, so here it can say the previous index now is the back index at offset KG. Then it says branch of greater than. The previous index is greater than 0. That means there's another one, because originally we said all indexes were 0. So when it gets back to the beginning, it'll be 0. So it can't go around anymore. And so, but it keeps going around here from one pole to another pole to another pole, using this information that was saved over here, this back information. Once it's finished with this, then it knows all the poles that are in the solution, and it comes down here, and one last thing it does is it moves the 100 values at pole needed to pole placed. That's probably pole placed is what it uses to display the answer. So this is the video on Trestle Dynamic Programming Routine.